in the analysis, because the fluid is in static. For the pressure, there is a force. That's all. So now, the second part of the lecture is about the fluid in dynamic. When the fluid moving from pipe to pipe or from the river or anything, so the earlier equation cannot be used. You cannot use P equal to rho G hash anymore. Okay, so that's why now you need the Bernoulli equation and also the energy equation. Okay, the first part of the lecture, which I hope everybody has watched the YouTube, is about how to analyze the flow rate. Okay, so you know that. Okay, this part, at least you know that in this analysis we use the continuity equation, which whatever mass come into the system, that will be the mass get out from the system. As we know that, I hope you guys still remember, m dot is equal to density time v dot. Okay, m dot is mass flow rate, and v dot is volume flow rate. So as you already know that m equal to rho time volume, so it also can be used here. M dot, the volume flow rate, the mass flow rate is equal to density time volume. So as we use in the continuous equation, the mass flow rate in will be the same of the mass flow rate out, and then this density, we assume that the density didn't change, so the volume flow rate in will be equal to volume flow rate out to the system. And everywhere, so everywhere in the pipeline, the volume or the mass flow rate will be the same. So okay, and then you already go through this part and this part to calculate what the flow rate. Okay, now we continue to the second part, is to use the Bernoulli equation here. Okay, the Bernoulli equation it's an approximate relation between the pressure, velocity, and elevation. When it is in moving, there is a different for pressure, velocity, and elevation. Okay, as with different pressure, different velocity, and with different elevation will occur to the system. They also happen with the velocity and also the elevation. Bernoulli equation only valid in the region of steamy, non-turbulent, okay, and incompressible flow, okay, and non-viscous. Okay, this is where we can use the Bernoulli equation. Bernoulli equation useful for flow region outside of boundary layers and wakes. Fluid motion is governed by the combined effect of the pressure and gravity force. Okay, this is the Bernoulli equation. So Bernoulli equation is this one, P over rho G plus V square over 2G plus Z, and it is constant. Okay, if you have a notebook near you, you can copy this equation. Actually, I hope that you can at least remember this equation. Okay, other than P equal to OG hash, you also need to remember the Bernoulli equation, P per OG plus V square over 2G plus Z, and it will be constant in the pipeline. Okay, what the Bernoulli equation is about? Bernoulli equation was derived based on the conservation of energy. So it is based on the flow energy and kinetic energy and also the potential energy. Okay, if you have take thermodynamics, they will add it will use the Bernoulli equation, but in thermodynamic they add hash. or hash is enthalpy. Okay, that is the energy that will change in doing a flow. Okay, static pressure is referred to the flow energy from the pressure. Dynamic pressure is designed for the kinetic energy, and hydrostatic pressure, this is present by the potential energy. Okay, and then statement. Okay, you also need to know that how to remove this part. Okay, in the analysis, okay, there will be some part. Okay, sorry. One of the usage of Bernoulli equation is to measure the velocity. So what you will be used is the pitot tube. So how they use the pitot tube is they insert a tube inside the line, and then they may and also they need to be one also the one other hole at the pipeline. So how they measure the velocity is by the measure the difference between these two lines, the piezometer and the from the pitot tube. And then from this difference, they can calculate the V. So why the difference occur? Because okay, when there is another tube here, okay, in front of the tube, it is assumed that the velocity is become zero. So for the P equal for the Bernoulli equation, okay, without the velocity, okay, so this is the part here. Okay, we will go to the example later. A Bernoulli equation, I think I have explained. A Bernoulli equation limitation. Okay, there is some limitation using the Bernoulli equation. First, it needs to be a steady flow. So unsteady flow can be used Bernoulli equation, and then it is a frictionless flow. Okay, every flow have some friction. Okay, at least from the pen, from the type of pipe or anything. But for Bernoulli equation, one assumption need to be made is there is no losses because of the friction. Okay, it just what is it? It's just an assumption here. But if you want to include the friction, okay, next week we will learn how to modify the equation to include the effect of friction. Okay, the third limitation is no shaft work. Okay, there is no pump, no turbine, or anything. Okay, if there is pump or anything, you need to use another equation. Incompressible flow. Okay, density incompressible. What will happen if the flow is compressible? If the flow is compressible, this density will change. Okay, that's why Bernoulli equation cannot be used in compressible flow. So it need to be a incompressible flow for this analysis. Compressible flow is normally occur when there is a nozzle when it is in the turbine jet or anything. So there is another equation for that purpose. Okay, no heat transfer. Okay, no hash. Okay, and then flow along a streamline. Okay, strictly speaking, the Bernoulli equation is applicable along a streamline. Okay, however, when a region of the flow is irrotational and there is negligible small vorticity in the flow field, the Bernoulli equation become applicable across the streamline as well. Okay, so you can use the equation along a streamline. Mean in one pipeline, as long it didn't have disturbance in the pipeline, so you can still use the Bernoulli equation. Okay, Bernoulli equation limitation. Okay, for this part, a long narrow tube, flow to a valve, heating or anything. Okay, in steady flow or non-viscous compressible fluid, the density, pressure and velocity and the elevation y, 2 points are related by this equation. Okay, I hope you have copied this equation. P equal over g plus v square over 2g plus z at point 1. Okay, this part here, where's my, okay, this part here is referred to the, is referred to the point 1. And this part here is referred to point 2. Okay, as long you got 2 points, and then you want to know to analyze the variation of pressure, velocity, or z, you can analyze using the Bernoulli equation. Okay, let's start the first example. A large tank open to the atmosphere is filled with water to the edge of 5 meters from the outlet tap. A tap near the bottom of the tank is now open, and water flow out from the smooth and rounded outlet. Determine the water velocity at the outlet. Okay, so this is 5 meters, and then there is a outlet here, and the first point is here. Okay, the first point is large tank open to the atmosphere. So what you know now is from this equation, when the pressure is 0 gauge, so you can assume that there is you can neglect the pressure part. Okay, so in the first part it is open to the atmosphere, or this part is P equal to 0 gauge. So that's why you can cancel the pressure part. 4.2, it is also open to the atmosphere. So 4.2, P equal to 0 gauge. So that's why you can cancel for this part. And then, okay, go to the velocity, and then compare to the velocity for both parts. Velocity at point 1, it is at the open tank. Okay, you can assume if the question didn't give you the diameter or anything, you can assume the tank is very wide. So you know that V dot, okay, V dot equal to V times A. So if A is too high, V become too low. Or for this analysis, when A is too high, V can be assumed to be 0. So for the equation, we can assume that V1 is equal to 0. So okay, you can assume V equal to 0 to any open part, open location, on the tank, on the river, and what else? Sea level or anything. Okay, so this part is when you can assume the V is equal to 0. Okay, and then what V2? Okay, V2 you need this is what the equation 1. Okay, the water velocity at the outlet. Okay, this is what we are searching to. We are searching this equation, and then we go to the Z. Z1 equal to 5 meter, and Z2 it now become 0. Okay, so you can cancel Z. So from a long equation, now the equation become only Z and also the V. The effect of elevation at point 1 and the effect of kinetic energy at point 2. There is no pressure effect and there is no elevation effect at point 2. So okay, this is the equation now. Actually the equation is from the Z equal to V2 square over 2G, and then now you need to V2 become the equation. V2 square equal to 2GZ, and then V2 equal to square root of 2GZ. Okay, so okay, after this simple equation, just include all the information. 2G is 9.81 and Z is 5 meter. Now we got the velocity 9.9 meter per second. Okay, so far? Any question? Okay, Shafiq. If you have any question, ask Shafiq. Oh, okay. Yes. There's a lot more. Okay, we go to the second example. A fluid constant density, 960 kilogram per meter cube, is flowing steadily through a tube. The diameter at the section D1 is 100 millimeter and D2 is 80 millimeter. The gauge pressure at point 1 is P1 equal to 200 kilopascal and the velocity here is 5 meter per second. What is the gauge pressure at point 2? Okay, so what the equation give? Didn't give the what's give? Okay, they give the rho. The density for the fluid is 960 kilogram per meter cube, and it's also give the pressure at point 1 P equal to 200,000 pascal. Okay, and it also give the V1 velocity at point 1 is equal to 5 meter per second. Okay, for point 2, oh, okay, what? This is the equation. Okay, so how to solve this equation? First, just rewrite the Bernoulli equation. P equal to rho g plus V1 square over 2g plus Z1 equal to P2 over rho g plus V2 square over 2g plus Z. Okay, this is 2, this is Z. Okay, please, I hope, okay, I made a difference here. Okay, so this is the Bernoulli equation, and then you know that the pressure at point 1, the velocity at point 1, and then for Z, okay, is there a difference for Z for elevation from point 1 and point 2 when this is a horizontal tube? Okay, when there is a when this is a horizontal tube, so Z1 and Z2 is same. So when it's same, you can cancel Z1 and also Z2. Okay, now this just a equation P V second pressure. Okay, you need to what is you need now, and then for the second velocity. Okay, what is the velocity at the point 2? Okay, how to get the velocity at point 2? Okay, you already know V dot at point 1 is same with the V dot at point 2, and V dot is flow rate. Flow rate is equal to velocity times the area at point 1 equal to velocity at point 2 times the area at point 2. Velocity at point 1 is 5 meter per second, and the area is pi times 0.1 square over 4 by d square over 4 equal to V2 that what we're searching now, and the area at point 2 is pi times 0.08 square over 4. Okay, you can calculate V2. Okay, how much is V2? Okay, you can cancel pi, you can cancel 4, so it just 5 times 0.1 square divide by 0.08 square. So what I got here is 7.8 meter per second. Okay, thank you. Thank you, Iman. 7.81 meter per second. Okay, now you got almost everything you need here. So from the Bernoulli equation, P equal to 200,000. Okay, make sure for every equation, use the SI. So for SI for pressure is Pascal. So make sure you use this 200,000 Pascal, not 200 kilopascal. Okay, divide by the density is 960 and G is 9.81 plus 5 square over 2 9.81 equal to P over 960 9.81 plus 7.81 square over 2 9.81. Okay, you can cancel 9.81 because it has in every equation. So now you're supposed to get the pressure, how much the pressure, and the answer is in Pascal. Okay, can anybody calculate the pressure? Okay, I think you can calculate by yourself. Okay, so is it okay for this example? Okay,
Sir, nak tanya sir.
yes,
Yang A tu mewakili area
area, yes, area.
Area untuk horizontal ke?
Area for the pipe. For the pipe.
Oh,
So for
pipe.
part 1, D1 is equal to 100 millimeter. So the question only give diameter for part point 1, the part here is 0.1 meter.
0.1.
Okay, for part 2, for this part, the diameter is 0.08 meter. So you need to calculate the area so you can get the velocity on the second part.
Okay sir. Thank you.
Okay, other question? Okay,
No, sir, no.
I think someone has calculated and give in the chat previously. So okay, I hope that that's the answer. Okay, we go to the second part. Sorry, third example. Third example, an open tank of water has a pipeline of uniform diameter leading from its as shown below. Point 1 and point 2 is open to the atmosphere. Mean P here equal to 0 and P here equal to 0. Neglecting all the frictional effect, determine the velocity of water in the pipeline and the pressure at point A, B, and C. The pressure here, and also the pressure here. Okay. So there is 4 question here: velocity of the water and the pressure at each point. Okay, so we start by looking the information that we got from the question. So for point 1, you already know the P. As it is open to the atmosphere, P equal to 0. And then it is at the surface of the tank. So for the velocity, how much is it? Okay, as described before, when it is at the open surface, assume that
Zero.
okay, yes, okay. Assume that the surface is too big, the A is too big, so the V now is become 0. And then for Z, okay, V equal to 0. And then for Z, the difference from point 1 and point 2 is 0.2 meter. So, okay, we can assume that Z here is equal to 0. So, Z here become negative 0.2. Okay, for Z, you can decide by yourself. So, if in case you want to decide that this is 0, so this one become 2. And this one become 1.8. Okay, you need to decide the elevation. The elevation, what is it? Where is that? So if this is 0, then this is the Z1, the value for Z1 and Z2. Okay, let's assume point A is 0. Okay, the bottom one is 0. So Z1 is 2 and Z2 is 1.8. Okay, velocity. Okay, we don't know, but this is what we're searching now. Okay, start for point 1 and point 2. Point 1, okay, P over rho g plus v square over 2g plus z equal to the P over rho g plus v square over 2g plus z. And this is for point 2. Okay, P per rho g, okay, 4.1, P equal to 0, and the velocity is 0, Z is 2. Okay, for this part, only Z and the value, and the value is 2. Okay, for the second part, P equal to 0, V, what we're searching, so V square over 2, 9.81, and Z equal to 1. V square is equal to 2 minus 1.8 times 2 times 9.81. So you got V equal to 0.2 times 2 times 9.81, 3.9, and then the square root is 1.98. 1.98 meter per second. Okay, you have answer for the velocity. Now we need for the point A, B, and C. Okay, let's start with point A. So we compare point 1 and point A. Okay, again, P over rho g plus V square over 2g plus Z at point 1 equal to P over rho g plus V square over 2g plus Z at point A. So again, P and V 4.1 can be neglected because the value is 0. Z equal to 2 equal to pressure 4.2 is what we're searching now, P over rho g. It is water, so 1000 times 9.81 plus V square at point 1. Okay, the value for V is equal, is same along the pipeline because it's given here the diameter is same, uniform diameter. So the velocity at point 2 will be the same to the velocity at point A. So the velocity at point 2 is 1.98 square over 2 times 9.81, and then plus Z. So Z at point A is 0. So you can get the pressure at point A. In Pascal unit. Okay, I think you can count by yourself the value. Okay, there goes for point B and point C. Okay, for point B, just compare. You can compare with between point B and point A, point B and point 2, or anything. So in case you want to compare point B versus point 2. So this is up to you. You can compare point 1 and point B, or point B and point 2, or anything. So point B, the pressure is what we're searching, over OG plus V. The value for V, what is it? Sorry, I think we'll start with the equation first. V square over 2G plus Z equal to P over OG plus V square over 2G plus Z. Okay, the pressure, there is a pressure at point B, which is this is what we search now, over OG, 9.81 times 1000 plus V square over 2G, 1.98 square over 2, 9.81 plus Z. Z at point B is, okay, use the equation that we used before. So this is 2 meter equal to P at point 2. Okay, the pressure is 0 as it is open to the atmosphere, plus V square, 1.98 square over 2, 9.81 plus Z. Z here is 1.8. Okay, so we can cancel now the part for V because the value is same, 1.98, 1.98. So now PB is related to the equation become PB over 1000, 9.81 equal to 1.8 minus 2.0. So it is equal to negative 0.2. So PB is equal to negative 0.2 times 9810 times 0.2 is equal to negative 1962 Pascal. Okay, if you want to check, you can do by yourself. You can compare from point B and point 1. Okay, you will get the same answer, PB equal to 1962. Okay, if you want to do it, if you want to try here, okay, I try to compare point 1 versus point B. So point 1, P equal OG plus V square over 2G plus Z equal to P over OG plus V square over 2G plus Z. Okay, don't get confused, Z and 2. I think my my handwriting here, 2 and Z is equal same. Okay, for point 1, P equal to 0, V equal to 0. And then for point 2, there is for point B, PP. Okay, and this is what we're searching. And there is a velocity. However, Z for point 1 and point B is same. Okay, in the same level. So you can cancel Z and Z. And now the equation become 0 equal to PB over 9.81 times 1000 plus V square is 1.98 in it, square over 2, 9.81. So if you calculate here, PB is equal to negative 1962 Pascal. So it is okay. You can decide by yourself to compare the point that you search which any point, as long the point that you compare has the most information that you know. Okay, like point one and point two, you already know the value of at point one, the value at point two, you can use that point. You cannot start with point one and point A or anything in the inside, because in A, B, and C, initially you don't know the P, you don't know the V, but when you know the V2, now you know the V at point C, B, and A. Now you can determine the pressure at each point. Hope it is clear enough to understand how to solve any Bernoulli equation. So is it okay? Okay, you can understand the Bernoulli equation? Any thumbs up? Okay, thank you. So hopefully everybody understand. Okay, the next example, example of application. Okay, this example I don't want to solve it here, but I have give you here the how to the scheme this schematic answer. So you can try by yourself. In case we have problem, you can contact me anytime. Okay, one more. To do the Bernoulli equation or any analysis, sometimes we need assumption. Okay, as an example for this analysis, water is flowing from the hose attached to a water main at 400 kilopascal gauge. Okay, the pressure of the water is 400 kilopascal. Yeah, P equal to 400 kilopascal. A child placed his thumb to cover most of the hose outlet, causing a thin jet of air spit water to emerge. Okay, if the hose is held upward, okay, the hose is held upward, what is the maximum H that the jet would achieve? Okay, before this, I has told you the analysis is valid in a pipeline. So if it's go out in the pipeline, so here the pressure will become the zero, and this is the end of the Bernoulli equation. But in some case, if the water made a straight line, okay, like you see here, the water look like it's still in the pipeline, although it is outside. So you can assume you can still use Bernoulli equation in this part. Okay, so this is the Bernoulli equation. So the pressure in both parts, you know that it is open to the atmosphere. So not open to the atmosphere. Only point one is 400 kilopascal, but point two is open to the atmosphere. And for the velocity, okay, velocity you can see here, the velocity at point one is almost zero, because the boy has covered most of the part with his thumb. So the velocity here can be assumed to be zero. Okay, Z1. Okay, we make it here as the datum. And then the pressure at point 2, okay, it's also zero. And then the velocity at point 2 is zero, because this is the maximum H that it can be achieved. Okay, I think for this, oh, this is 400 kilopascal gauge. Okay, no need for the PATM. You can cancel for this part. Okay, okay, here it's got it cancel the P1 equal minus PATM is equal to P gauge, and then using this information, you can get the Z become 40.8 meter. Okay, hope you can understand why in some case in some cases there is needed for assumption. Okay, let's try another example. okay, the water level in a tank 15 meter above the ground, okay, 15 meter above the ground, a hose is connected to the bottom of the tank, and the nozzle at the end of the hose is point straight up. The tank cover is airtight, and the air pressure above the tank level surface is at 3 atmosphere or 300 kilopascal. The system is at sea level. Determine the maximum H to which the water stream could rise. Okay, the same question as before. So although this the pipeline is until here, but as the jet here look like still look like a pipeline, so you can assume here the pipeline you can use still use the vanilla equation from this point and up to this point, okay, at the point here, point 2. Okay, still use the Bernoulli equation. P equal to P over OG plus V square over 2G plus Z1 at point 1 equal to P over OG plus V square over 2G plus Z2. Okay, Z and Z. Okay. Okay, pressure at point 1, it is 300,000 over OG 9 sorry 1000 times 9.81, okay, plus V 8.1, okay, it is at the open tank, so you can assume neglect the V effect of velocity, plus Z, the elevation at point 1 is 15 meter, okay, you can assume 15 meter is the same H of how many, five level of a building, equal to P2, okay, the maximum here P equal to 0, and velocity is also 0 at the maximum. 0 plus 0 plus Z, okay, Z2, this is what we're searching. So okay, you can calculate, and hopefully you get Z2 is equal to 45.6 meter. Okay, you can try. I hope there's no mistake for the answer given. This okay for this part. Okay, this two part, this assumption is needed in your assignment. Okay, keep annotation. Okay, if you go to the assignment, where's the assignment? Download. For this assignment, okay, if anybody have read the assignment, okay, what you need to do is you need to make two pipeline. Okay, the pipeline here is using the hose. I think what Mr. Rizam has do to you is a bit easy to handle, because this is what you need. And then even if you want to search where to buy, I think it has give where is it, Shopee. Okay, so in case you want to search where to buy, there's also here, and you can search by yourself if you want another link. Okay, so what you do is make a pipeline and then compare with these two example. The first pipeline is straight and the second is a closed loop. And then compare the flow rate of the from the what is it from the uh, hose from the outlet here. Okay, compare the velocity at each point. Okay, to do the analysis, you need to know the pressure at your house. Mean the pressure from the pipeline in your house. So what you need to do is you need to get the pressure, okay, at the pipeline. So how you get the answer is by connect the hose to the pipe and your pipe, and then do the same as the example before, and measure the H, the maximum H the water can achieve. And then from this experiment, you can get the pressure and at your for your for the pipeline at your house. Okay, so you need the data to for this assignment. Okay, hopefully everybody can understand. Okay, continue our lecture. Okay, the last part is the hydraulic grid line and energy grid line. Okay, for the hydraulic grid line and energy grid line, it's just information that you need to know in case you come to practice. Okay, in case you work with the syarikat air or anything. So to for the fluid from a tank to the household or anything. So HGL is EGL is the what is always used. Okay, normally engineer like illustration. Okay, they didn't like the value or anything. So what they look at any point is the HGL and EGL. Okay, HGL is the line that represent the sum of the pressure head and the elevation head. So you know that for the hydraulic line, it is the sum for P over G plus Z only. For the energy line, it's include here the V, this the effect of kinetic energy. So this is the difference with the HGL and EGL. So to get the velocity at each point, so what as look at as is the difference between the HGL and EGL. If the difference is big, the velocity here is big. But if the difference is narrow, and then the velocity at this point is weak. Okay, this is how engineer normally determine the location where there is problem with the of the flow rate at any point or anything. Okay, HGL and EGL, there will be effect for pump and turbine. Pump will increase the pressure, the head for the HGL and EGL, and the turbine will decrease the value for HGL and EGL. Okay, that's for HGL and EGL. I think you can read by yourself. Okay, last thing is velocity measurement by a Peter tube. I've told you we will discuss about it. So okay, so this is the pitot tube and this is the venturi tube. The difference is 12 centimeter, and at the ventrimeter the H is 7 centimeter. Okay, the pitot tube was insert 3 centimeter inside the pipeline. Okay, to get the value here, still use the Bernoulli equation. Okay, for easier is you need to remember only one equation is the Bernoulli equation. So okay, you got here that at point 1 P V N Z and point 2 P V N Z, but at point 2 it is in a stagnation point. Okay, because of this tube, the velocity of the water in front of the tube is assumed to be 0. So, okay, you got now V1 over 2G equal to P2 minus P1 over rho G. And then for the pitot tube and venturi tube, the water is assumed to be static. So you can use here the P equal to rho GH again. So as you have measured the P equal to rho GH at point 1 and point 2, now using this equation, you can determine the velocity of the pipeline. Okay, that's all for today. Okay, this is summary. You have understand the conservation of mass, linear momentum equation for the Bernoulli equation, and conservation of energy. And this is also what you learn from the lecture these 2 weeks, this week and previous week. Okay, any question?